Okay, we are on the cross section of the volume flipbook. So it is actually going to be page 2. So assuming this is page 1, you open it up, it'll be page 2 and page 3 that we're working on today. Okay, all right, let's get going. So what is cross section? Cross section means that you have this two-dimensional picture that you put on the ground. It's your base. It is the bottom of your shape. And then from that base, you're going to build something three-dimensional on top of it. And so when you cut it on the side, these are cross sections. And when you cut it on the right way, each cross section will be the same shape. So for example, something that you see very often is something like, oh, I have a circle as my base. And because it's three-dimensional, it doesn't look circle because it's flattened on the floor. It's flattened out. And then on it, maybe I build triangles. And see, if you build triangles, as the diameter increases, you're going to have bigger triangles, and as diameter decreases, you're going to have smaller triangles. So it's going to be a curvy triangle like so, right? What I tell students is this kind of looks like the Sydney Opera House, right? So again, there's a lot of things you can kind of relate this to, but it's a little harder to picture the full image. However, one cross section is easy to see. So again, you always have a base area. So a base area could be made with, I don't know, a trig function and a linear function. So it looks something like that. And then from there, you're going to build semicircles. Semicircles, going to build this way. Semicircles, 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 right? So your semicircle is going to be bounded between your function here, this top and this bottom here. So again, our top and bottom is very important in this case. Okay. All right. So let's take a look at some of the examples we have here. So it said the solid lies between the planes perpendicular to the x-axis at x equals 0, x equals 4. The cross section is perpendicular to the x-axis. So this is the most important thing. Whatever it is perpendicular to, that's your d whatever. Because it's perpendicular to the x-axis, my x-axis is here. I'm going to be perpendicular to it. Notice how I'm growing this way. This is a dx problem. If this is a y-axis, I'm perpendicular to the y-axis, and this is a dy problem. So whatever you're perpendicular to, that is your derivation variable, okay? All right, so this says you can look at your equation two ways. You can look at it as x equals y squared, or you can look at it as two functions here. Y equals negative root x, y equals negative root x. And then the other way is y equals positive root x. Y equals positive root x. And the reason why we want to rewrite it as an x function, as a y equal function, is because it's a dx problem, right? So it says the cross section of this is our circular disc with diameter on the xy plane. Basically, we're building circles, a full circle. So notice how these circles, and there's infinitely many more in between, I just don't show it, right? Infinitely many more. In fact, if you fill this out, this becomes a bullet, right? It's a rounded thing down here, up here, and it's a rounded thing, it's a bullet, right? Now, notice each of these circles, what is happening, what is important in the circle. So I try to give you some advice on how to start a problem like this. So first you graph your base functions, right? Here's your steps, which we already did. We transport the function to a 3D plane, which we're going to do in number 2 here. But number 1, this is already done for you, kind of like a training wheel. Determine the shape of the cross sections and the axes are perpendicular to. So first of all, we already know this is a dx problem, right? Because we are perpendicular to the x-axis. So the volume of this is something dx, right? We're adding up infinitely. That's the integral for. What are we adding up? Well, this is a circle. So the area of a circle is pi r squared. Notice the only unit I need is radius. So now let's look at how the radius is defined in this picture. The radius is right here in this circle, in this circle, in this circle, and in all the circles subsequently. So the radius is bounded by this function only. So therefore, that is my radius. I don't need the other half because it doesn't play any role in this picture. All right, so the area of this particular circle, bounded by these two functions, is going to be pi root x squared, which then provides to be pi x. So I'm adding up infinitely many of these circles, pi x. From where to where? It tells you from x equals 0 to x equals 4. Those are my intervals, x equals 0 and x equals 4. And so then you treat the pi like a coefficient. You put the pi outside, 0 to 4, x dx, pi x squared over 2, 0 to 4, which then becomes pi 16 over 2. This thing has a volume of 8 pi, okay? And that is the volume of this particular bullet. All right, so on the same base now, we're going to build something different. We're going to build squares here. Their perpendicular cross sections are squares here. So then I write myself a note. What is the area of a square? Well, the thing that's particular about square is that all the sides are the same. So instead of base times area, base times height, we're gonna have side times side, right? So it's gonna be side squared. So then we need to figure out how is each side contained in this case. So notice how each side goes from here to here. I'm restricted from here to here. So if you refer to what we drew on the previous problem, this is y equals positive root x. This function down here is y equals negative root x. So my side is going to be top minus bottom. It is restricted top by the pink root x and bottom by the green negative root x. So top minus bottom in this case will be root x minus a negative root x, right? So each side in this particular picture is going to be 2 root x. So if I take that and plug it into my area equation, each side is going to be 2 root x squared. Don't forget to square the outside, that's 4, square the inside, that's x. So the volume of this really weird shape is going to be squarish on the bottom, but kind of rounded out in the front. The volume of this is going to be adding up infinitely many squares, this type of square, the 4x squares. It's a dx problem because I'm still perpendicular to the x-axis. And I'm integrating from 0 to 4 because that's the beginning where I start my function and end my function here. And that's it. You can pull the 4 outside if you want to and just have this function here. So 4 x squared over 2, 0 to 4, you get 4 times 16 over 2. This is a very nice volume of 32. Very clean answer, which we rarely have at this point. Okay. All right. So now what do we do? How do I see this myself? Okay. So let's start with says a solid has as its base in the region of xy plane bounded by the graphs of y equals 4 and y equals x squared. So here you gotta draw yourself either a game plan or know what the shape looks like. So for me, I do a really two-dimensional picture here. Y equals x squared looks something like this. Y equals 4 will cap it out. So that's my region. So then I'm going to take this picture and basically flatten it out. So that's what is happening here in my picture. This is my x-axis, this is my y-axis. Now, sometimes your textbook or other resources you find online will have the x and y-axis flipped around because it makes it a little bit easier for you to draw your cross sections. But I feel like this type of graph makes it easier for you to see. You simply take your function, your xy that's facing you right now, and you flatten it out. And now you have your z-axis going up and down. Okay. So now if I were to graph this, right, typically 0, 0, right? This is my 0, 0. 1, 1, that's my first point here. 2, 4, 1, 2, 3, 4, 2, 4. Negative 1, 1 is here. Negative 2, 4 is here. So this parabola, yes, even though it's a parabola, it's going to look a little lopsided because, again, it's three-dimensional. So it's going to look something like this, right? Okay, and then I'll erase what I don't need. Okay. And then don't forget your y equals 4. So that's the boundary of my function. Okay, now perpendicular to the x-axis. So if you continue reading, blah, 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 cross sections are perpendicular to the x-axis, right? So cross sections are perpendicular to the x-axis. Therefore, it's a dx problem. What am I building? I'm building circles with a diameter on the xy plane. So an easy way to do this is to look at my graph here. Since it's perpendicular to the x-axis, any of my y lines, any of the vertical lines are going to be perpendicular. So I'll pick one of those lines, one of those gray lines I see here. I'll pick one of those gray lines to show that that's my diameter and draw a three-dimensional circle. So again, when I say three-dimensional, it's going to look lopsided because it's not like a real circle because it's three-dimensional. So that's a circle for me. Okay. But what is the key point here? First key point here is that now we have established that I am dealing with circles. So area that I'm dealing with is the circle, pi r squared, right? And then how is my radius? Well, I don't know my radius yet, but I do know my diameter. So my diameter in this picture is bounded by the top function minus the bottom function. The top function is 4, bottom function is x squared. I know my diameter is double my radius. So if I take that function divided by 2, I'll get my radius. So radius is going to be 4 minus x squared over 2. Okay, so If I take that, plug it back into my function, my area is going to be pi 4 minus x squared over 2 squared, pi r squared, right? So if you can, personally, I would work it out so I can take out as much coefficient as I can so I don't have to work it out in my integral, right? So if I do so, I get pi over 4 because the 2 squared on the bottom becomes 4. And I have 4 minus x squared squared, right? So the volume of this is adding up infinitely many of my circles, pi over 4, 4 minus x squared squared dx. From where to where? Well, look at my x-axis. I started at -2 and ended at +2. Could you double this and make it go from 0 to 2? Yes, you can. But again, if you want to err on the side of caution, then you don't want to do the doubling. You can really do from -2 to 2, and that still works. Okay, so I'm going to double that and make it pi over 2. 0 to 2. I'm going to multiply out this integral in here, my integrand. So it's going to be x to the 4th minus 4 times x squared, double that. So 8x squared, and then 4 squared is 16 dx. Okay. All right. So that gives me pi over 2, x to the 5th over 5 minus x cubed over 3 plus 16x. E value is 0 to 2. And I like this because I don't have to plug in the 0. So it's pi over 2, 32 over 5. Minus 64 over 3 plus 32. So pi over 2. Oh, my common denominator is a 15. Oh, that is a fun one. So my common denominator is 15. We get 96. Yeah. Minus 320 plus 480 over 15. Just gotta quickly check I got my multiplication correct. Yes. All right, so minus 320 plus 96, I get pi over 2 times 256 over 15, which makes it 128 pi over 15 cubic units. Really lovely answer, right? Yeah. Okay. All right, back to the ugly answers. Okay, the good news is we're using the same base area, so practice that one more time, drawing that parabola here. So 0, 0, 1, 1, 2, 1, 2, 3, 4, negative 1, 1, negative 2, 4, my parabola here, and my parabola here, and my y equals 4. Okay, this time what am I building? Ooh, I'm building equilateral triangles with its base on the xy plane. An equilateral triangle with a base on the xy plane looks something like this. Now, it may not look equilateral, but I'm forced to be equilateral. Now, you may or may not know this, but equilateral triangle has a formula of its own. If you don't know it, you can A, derive it, B, look it up, C, memorize it. So, your choice, right? So, the area of an equilateral triangle, it's not 1/2 base times height, is √3 over 4 times the side squared. This has to do with the fact that this is a 60, 60, 60 triangle, and then you cut it down the middle, it becomes a 30, 60, 90 triangle. If you want, we can definitely go over this when you have time, but right now, in the interest of this, we will continue. So how is each side bounded? So each side is bounded same way as before, bounded by the top function and the bottom function here. So each side is top minus bottom, which is 4 minus x squared. I don't need to divide by 2 this time because I need the full side. Last time I divided by 2 because I wanted the radius. I didn't want the full side, I wanted half of it. This time I want the full side. Okay, so then I can use that and plug it back in. So area of a triangle, or equilateral triangle, is going to be √3 over 4 times 4 minus x squared squared. Okay, so the volume of this is adding up infinitely many, √3 over 4, putting my coefficient there. So messy, try it again. All right, putting my coefficient in front, √3 over 4, negative 2 to 2, 4 minus x squared squared dx. Okay, all right, same as before, because it's symmetrical, I can double this. So it's going to be √3 over 2, 0 to 2. Multiplying this out, I get x to the 4th minus 8x squared plus 16 dx. Right, very similar to the previous problem because we have the same functions. Okay, so √3 over 2. Take your antiderivative. E value 0 to 2. Okay, all right, so √3 over 2. 32 over 5 minus 64 over 3 plus 32 minus 0. Hey, it does not look like exactly the same as before. So this will give me √3 over 2 times 256 over 15 This one's a really cool answer, pretty much the same as before, but except this is 128 root 3 over 15 for my cubic units. Okay. All right, so really try to practice drawing these three-dimensional graphs. You start with the 2D first, flatten it down, make it 3D. I have blank 3D graphs on the resource modules on Canvas for you. So make sure to print a few out or have them ready for your homework for this section. Okay, all right, that's it.